This is Dr. Mad. Maybe you're like me, well, not exactly like me, God forbid, but I mean, maybe you've read like me stupid things, crazy things, right things, wrong things about quantum mechanics. And you want, like me, to figure out exactly what's going on. So what we're going to do is, first of all, understand why quantum physics is so weird. And two, if it's really better than, more classical theories. So that's what we're going to do. But for that, we need some math tools. So I know some of you will go, ah! But that's okay. Don't worry. We won't use very complicated mathematics. And also what we'll try to do is to explain why we use some tools and how we use them, as opposed to just use, formulas. So the basics we need to talk about are derivatives and integrals, vectors, trigonometric functions, fields, electromagnetic waves, and finally the Maxwell laws. The first time you look at the Maxwell laws, it's like this. You say, ah! and then eventually, as we will see, it's not that complicated, and we can explain everything that's written in there, so don't worry. Once we have that, we'll see where we go. But anyway, these are the tools we need. So let's start with the derivatives. Derivatives are used to calculate variations, how something evolves in time, for instance, like if we have a function that gives us a position of an object, the derivative of that function will give us the speed because it will give us the rate of change of the position in time. And similarly, the derivative of the speed will be the acceleration because it gives a rate at which the speed goes faster or slower, okay, etc., etc. So that gives you an idea of what derivatives are. Integrals is just the reverse. What I mean by that is that derivative of the integral, or the integral of a derivative of a function, is equal to the function itself. Now, how do we define that? Well, there are many ways to define the integrals. One example is here, if you have a curve here representing a function on a given interval, here from 0 to 2, you have to look at the area which is below the curve here. I'm assuming it's a positive curve like it is here because it's x squared. And let's do some quick animation there. Here you go. And put some rectangles here. And as you can see, the more rectangles you have and the closer you get to fill in the whole area here. And that's what we're going to do. And we're going to use this formula here, which is a sum of all the areas, all the surfaces here of all the rectangle, which eventually will completely fill in, as we increase the number of rectangles, this area. So basically the integral between two numbers, a and b in this formula, is just equal to the sum of the height of the rectangles multiplied by the width of the rectangles here. So one obvious application is to calculate areas, but you can also use that to determine an average value. Like, for instance, the formula for an average value of any function would be something like that, And then when you apply that formula, knowing that the integral of x squared is x cubed over 3, you get this result here. And so that means that the average value of x squared between 0 and 2 is equal to 4/3. So these are examples of how we use integrals, okay? Next thing, vectors. Let's take an example. We have a point here in space and we want to determine the position of this point. What we can do is use a reference that I call O here, which will be the reference 0, and from there I can define a height, can define a width, and I can define a depth, and then I can use that to say, okay, my point P here is 5 units high, 3 units wide, and a 2-unit dip in that direction. And that gives me exactly the place where that point is. Another way to do that is to use an arrow here between 0, the origin, or call it O, and the point P here. And you get something, that goes like this, roughly. This is equivalent of what we call a vector. And this vector, again, will be defined by 3 numbers here. And these numbers correspond, obviously, to those directions, in the axis. And so I can say that the vector OP is equal to 3, 5, 2. And as you can see, the order here is important, will be important, has been important, will always be important. Okay. So that's for a special type of vectors. Of course, you have many types of vectors. These are called 3D space vectors. So the vector space is a 3-dimensional space. And the numbers here are part of a structure called a field, which in this case is just numbers, And these coordinates here that completely define the vectors for this particular example, of course, are called scalars. In that case, scalars are just numbers, okay? So that's how you use vector and loosely define them. Now, vectors are part of what we call vector spaces. And those spaces have some specific operations you can use on them. For instance, like the simplest one would be the addition. So let's assume you have a vector u here. It's called u. Not u, the u, the letter, of course. Actually, it's crazy. And then you have another vector v here. Now I want to define what u plus v would be. Then what I do is just that, and I get a vector here w, and I can say w is equal to u plus v. And that is more formally defined here. Let's assume that u has u1, u2, u3 coordinates, and v1, v2, v3. Then w will have u1 plus v1, u2 plus v2, and u3 plus v3. And, I told you it was simple. Okay, now if you repeat that addition, you can multiply vectors by a number, by a scalar. So in that example, for instance, you can see that the vector v multiplied by this scalar here, this number here, lambda, will give you this vector w with those coordinates there. So as you can see, when you do that, you don't change the direction. The direction is like this. You don't change the sense unless lambda is negative. But what you do is you change the length. And usually when you use vectors, the length of the vector defines some kind of amplitude of a phenomenon, and so that's obviously very important. Another type of operation you can make on vectors is called a dot product. And it's also called sometimes scalar product, but that's a bit confusing because you can confuse it with the previous thing, the crazy mathematician. Anyway, this one is different. In this one, you multiply 2 vectors, and the result gives you a scalar, a number. So for instance, the dot product of vector A by vector B is equal to a number here. And that's a bit weird because usually, when you multiply 2 things, you get, the same type of thing. But here, no. And we'll see in a while why we do that. So in order to do that, in order to define exactly what S would be, we need to define more functions called trigonometric functions. So I know trigonometry sounds like a complex name, but in fact it's very simple. It means measure of triangle in Greek, and because it was invented by the Greeks, of course. And basically that trigonometry regroups, functions and rules involving angles, and that's very key because angles are important in physics, as we'll see soon. We'll only use 2 simple functions in that field. One is called the sine of an angle, and the other one is called the cosine. And you can define it in two different ways, you know, the regular way like this. So as you can see, something very regular, which actually seems to repeat itself. And what I mean by that is that, you know, it goes up and down, and then again up and down, and again up and down, what we call a periodic function, because it comes back always to the same thing. So some clever guys, you know, say, well, you know, it looks like a circle, because the circle is very regular, just like the sine is, and also it, you know, the function repeats itself again and again and again. When you come back to this value here, you do again the same thing. And as you can see, the height here seems to correspond to your point here, and you can actually see that here a little bit better. So the circle here is here, and as you can see, you know, if you move that a little bit here with an angle there, the sine by definition will be equal to the ratio between that side here of the triangle over that side. Now usually we use, at least to define the sine and cosine, we use a circle here with a radius equal to 1 unit. So that length over 1 is just equal to that length. So that means that the sine here is equal to the point there, okay? Or the point there is equal to the sine here. And cosine would be the same, except instead of using that side here, we'll use that side here over that side. And as you can see, the result is quite similar, except there's a little shift between the two, which we call the phase. So overall, as you can see, it goes up and down, and then comes back and start again and again and again. And so, as you know, probably, you know, the perimeter here of the circle is equal to 2 pi r, 2 pi times the radius. So if the radius is equal to 1, so that's 2 pi, you know. So when the angle reaches pi over 2, the sine will be equal to 1. And if the angle is equal to pi, the sine will be equal to 0. And then we'll go down here. If the angle is 3 pi over 2, then it will become -1 and finally go back to 0. Okay, I think it's clear enough, okay? So that's enough for those functions. The only thing we will look at now are what we call remarkable identities. Nothing to do with passports or something, you know, nice about the picture. No, it means that we have special formula that we're going to use later in our derivations. So we just remember those, you know, sine square plus cosine square is equal to 1, always. You know, whatever angle you take, this is called theta, by the way, that's a Greek letter that we use for angles, don't ask me why. So that means also that the average of over a period of the sine square is equal to the average of cosine square, which is equal to 1/2. Another interesting formula here that we're going to use later is cosine square minus sine square is equal to cosine of twice the angle here that we used. Okay, and finally we'll have to remember that the derivative of the sine function is a cosine function. I'll let you derive that. And also the derivative of the cosine is a minus sign. There's a catch here. Cos, sin, minus sin. Ooh. Remember that. Anyway, since we've seen that the integral was the reverse of the derivative, then the integral of cosine is sine and the integral of sine is minus cosine. Okay? Okay. Now that we have defined these things about sine and cosine, we can go back to the definition of our dot product. The dot product of two vectors, as I said, is a number. So here we're going to use the length of A and the length of B multiplied by a cosine of the angle between A and B. So that will be a number, which is normal because the scalar product is a number, remember? Yeah, remember. Okay, good. So now how are we going to use that? Oh, yeah, first of all, I'll let you do that as an exercise. It's fun. If you assume that A is equal to A1, A2, A3, and B is equal to B1, B2, B3, then the scalar product will be equal to that. So that's what we write here. You know, it's equal to the sum of the products of the coordinates. And I'll let you derive that by yourself, or you can cheat and go to internet, or you can just trust me, or any math books for that matter. How are we going to use that? Well, it can be used, for instance, in what we call the scale projection. Now imagine you have a vector here, and if you do perpendicular here from the horizontal axis, the scale projection will be equal to A multiplied by cosine theta. Okay, that's obvious if you know the definition of cosine that we've just seen before. So if you followed, that's what you'll see. Now, how can we use that? Well, for instance, let's take an example. You know that vector represents a strength, a force here on an object. Okay, you want to drag this object using the B force here in that direction, the horizontal direction, and then you want to apply another force. Another force will be called A, which makes an angle here with B. But as you can see, the angle here is not very high. Well, if you use the scalar product of these two vectors, you will get something that will be equal to the product of the lengths of A and B multiplied by the cosine. And the cosine here will be pretty big, you know, pretty close to 1. So you will have a big scalar product. And therefore, that means that there will be a strong influence of A over B. And so A will help to pull that object here in the same direction as B does. On the other hand, if A is perpendicular to B, then the cosine of theta will be equal to 0. So the scalar product will be equal to 0, and that means there's no influence. You know, A will not have any influence to drag the object in the same direction as B, and vice versa, of course. And finally, you know, if A goes in the other direction, then the cosine of this angle here will be negative. So that means that it will be basically opposed, you know, and we'll try to pull it on the other way, and we'll have a lot of influence, and you can calculate that influence using the scalar product. So that's something that we'll see we'll use later in our derivation. But remember also the definition of what we've seen before regarding that scalar product. And finally, the last operation we're going to look at, it's still another product, but this time is a true product. What I mean by that is it's multiplication of one vector by another vector yields to a vector. Oh, good. So how does it work? Well, you have vector A, you have vector B, and by definition, the cross product will be that vector here. Now, by definition, what I mean is that we're going to define the direction of that vector, the sense, and also, of course, the length. And so let's start with the direction here. Well, by definition, the cross product is always orthogonal to the two vectors. What that means is that it's perpendicular to the plane that they define. Okay, so that's the first rule that defines the direction. The second rule is the sense, you know. Okay, it's that direction, but is it up or down? Well, in that case, it will be up. But if you use B cross product A, it will be in the other direction. It will be like this, okay? So that means that as opposed to what happens with numbers, you know, 3 by 5 equals 5 by 3. In case of vectors, that's not true, you know. A cross product B is equal to minus B cross product A. So it's different. So we've defined the direction and the sense. Now we have to define the length, you know, the module or amplitude or whatever you want to call it. And so it will be defined like this. It will be defined by the length of A multiplied by the length of B multiplied by sine theta. So why is this definition and how can we use it? Well, let's have a quick look. But before that, I'll let you derive this formula here. So again, if we assume that A is equal to AX, AY, AZ, and B is equal to BY, BZ, BX, BY, BZ, then P will have these coordinates, okay? So I'll let you derive that. It's fairly easy. If you, again, you can go on internet or any math books, it will explain to you how you get to that based on this definition here. Okay, so now that we have this, let's have a look at what happens. You know, here we have two vectors, a green one and a red one, and the blue one is actually the cross product of the two. So let's take a closer look at what's going on here. You know, there is a lot of information that the cross product here, the blue vector, gives us. For instance, we can see, you know, kind of a rotation here, and the cross product actually gives us the axis of the rotation. Another information is that depending on the length of the cross product, we can tell, you know, how perpendicular, how orthogonal the two vectors are. And also, the fact that the vector goes up and down tells us whether the angle between the two vectors is increasing or decreasing. All of this information data will help us when we talk about the, you know, movements of particles in a field, you know. The suspense here. Well, let's not get ahead of ourselves, okay? And let's move on to the next slide before you get hypnotized and fall asleep. I'm so funny. Okay. Talking about fields. So here we have a field, you know, and the field here in that case would be a surface where you can, you know, walk like this, or you can walk like that. But here it would be a shame because you would crush some of the nice flowers like that. But anyway, I'm a poet. I'm French, you know, so I'm a poet. Anyway, so here we can see that on every point of the field, which is a, you know, let's assume it's a flat, you know, two-dimension surface, we have a different flower here, okay? And so on every point of that field, we can define something, you know, which would represent the flower that we have here. Actually, we can do something even more interesting here with different types of flowers and different colors and different height, whatever. And so for each point in the field, in this 2D surface, we can define, for instance, which color of the flower is there, or what is its height, etc., etc. Now, and of course, in mathematics, it's a little bit less poetic, but this is an example of a two-dimensional field. What that means is that, you know, we have an area here, which well, in that case would be a 2D area, and for every point in this area, in this field, I define a vector here that gives me some information, you know. So in that example, the field is a function between R2 and goes to R2. In other words, for every point in R2, which has two dimensions, you know, because you have height and width, you will get a vector which also has two dimensions. Now let's see how we can use that and a scalar product to have some fun here. So, I love this one. By the way, all the animations I use and the graphics, etc., I'll give at the end of the video series, I will give you some links where you can have a look and see where I picked those from. Okay, so, well, let's just animate that. So let's assume we have a field like this, you know, anytime now. Yeah. And in that field we have a particle here which goes on this row there. And we want to know what influence these little vectors here have on the way the particle will go. we're going to use the scalar product, okay, between the particle's velocity and the field. And here you see at the beginning the scalar product is pretty high because in fact the particle starts in the same direction as the arrows we have in the field here. So there's a very strong influence of the field to help the particle to move. On the other hand, here we get to zero because we arrive at that part here where the arrows in the field are perpendicular to the movement of the particle. And here it gets even worse here, and we get about here, I guess, because the arrows here and the vectors in the field are in the opposite direction to the movement of the particle. So it will have a strong influence against the movement of the particle, etc., etc. And so by just looking at this function, which is a scalar product here, or these areas, which by the way are called curved integrals, we'll know exactly what's going on. And that represents clearly what happens here when a particle moves in a field. So that will be very interesting, as we'll see soon. I'm sure you're fascinated, right? Right? Yeah, that's what I thought. Anyway, now that we've talked about fields in general, I'll go back to the world of physics in the 19th century, where there were a lot of discoveries and experiments made with magnets, for instance. Magnets were discovered a long time ago by the Greeks, because there is a region not far from Greece, actually it probably was part of Greece at that time, which have a natural ability to attract or repel each other. Or, they had these swords, and when they got near the stones, the stone was attracted. Okay. And this is called, we learned later that this was caused by electrons which are in a certain way. Actually, that's one of the theories. Another way to create a field like that, as opposed to just a pure magnet, is to have a current flowing, an electric current, of course, flowing in a conductor like this. And then there will be a magnetic field around the conductor. That's another way to create some magnetic field. Now, the other type of field that I want to talk about is the electric field. So that's, when we discovered that matter was made out of atoms themselves, made with protons, neutrons, and electrons. I'm talking about, 19th, 20th century. There were some charged particles called electrons for negative part and protons for positive parts. And what was interesting is that the theory shows us that the particles with the same sign will repel each other because of an electric field like that, which is called a Coulomb force field. And on the other hand, when the particles are of opposite sign, positive with negative, they will attract each other. In the 19th century, there were a lot of experiments made on electricity, magnetism, optics. And there's this guy, James Maxwell. Maxwell was a Scots guy, and as a big fan of Maxwell, I really want to set a toast to Maxwell, because he was a great Scotsman, and every time I talk about him, I'm so moved that I need to take a toast for him. To you, Jimmy. Not Jimi Hendrix, Jim Maxwell. I always feel smarter, when I think about James Maxwell. Anyway, so Maxwell derived these 4 equations which combine everything together. Electricity, magnetism, and optics. That's why even after 150 years, it's still applicable, and that's wonderful. You know what he did, really. Maybe, well, yeah, no, I'll later. You know what those four equations that he defined, and we're going to see and have a look at, actually are still used today. You know, for television, for mobile phones, for Wi-Fi, anything that's lights. You know, anything you do with light, all of this is just derived by the four equations by Maxwell. So that's pretty amazing. And so what Maxwell proved was that light, or discovered rather, was that light was actually an electromagnetic wave. So what is an electromagnetic wave? Well, it's a combination of an electric field and a magnetic field. Here we have some typical example. I mean, they're not all like that, but this is a typical example of a monochromatic linear polarized plane wave. Don't ask me what it means. Well, basically it means it looks like that, okay? And here you can see there is an electric field that goes vertically. There is a magnetic field that goes horizontally like this, and both, you know, move like a sine function. And actually they represent an electromagnetic wave or light wave, which is the same thing. And this light wave moves that way. Okay, so here's the direction of propagation of the light wave, and with that you can see that there is an electric field going that way and a magnetic field going that way, and oscillating like this. And we're going to use that to prove all the things we need to prove using the Maxwell equations. Okay, isn't that fascinating? If you look at this for half an hour, I can guarantee you can sleep. Anyway, so that was the tools we needed, you know, the mathematical tools we needed. Now with that we can explain the Maxwell equations and then all the things we need to do in order to prove Bell's equations later. Ooh, that's so much fun. I love that. Don't you? Yeah, you do. Yeah, you do. Okay, well, in any case, here's to Maxwell.